All right, I'll just record this for posterity in case anyone's watching. So last time I talked about these ions. I might just get this into shot. No, I'll keep it there. Okay, so last time I talked about the polyatomic ions that you can get that form. I also mentioned the structure that held the ions in place. It's a 3D lattice. Okay, looks kind of like this. If you can imagine the cube, they arrange themselves negative, positive, negative, positive, negative, positive. It's so that because of those charges, to prevent repulsion and maximize attraction, they form this three-dimensional, what we call a lattice. So that's repeating units. In the notes I put on DayMap, you can see that a bit more clearly, okay? So please get on that and make sure you'll familiarize yourself with the structure, because it's kind of leading in, excuse me, what we're talking about today. Yep, Craig.
Elements that don't bond with each other.
Any elements that don't bond with each other? Who can help them out? Which elements don't bond?
Noble gases.
Noble gases, good. So basically helium, neon, argon, krypton. Xenon's weird. If you get it under certain circumstances, it will bond kind of. But most of those don't. All right. In fact, as a rule, they don't at all. It's when you start messing with the nuclear particles of xenon that you can start doing fancy things with it. But it takes a lot of energy to do that. So, no, they will not react. Gold is hard to react with, but it will do so over a long period of time. Okay, if you've got a strong acid, it will dissolve. And it won't react with oxygen, of course, but if we left it out in the rain for, years upon years, it will eventually oxidize. All right. So this table I'll give to you as well. This is on DayMap 2, the table of common ions. I'd like you to familiarize yourself and the charges on those ions. Now, most of the charges are informed by the periodic table, as we know, but just get an idea about the more polyatomic ions and those transition metals to help you. So, things to point out: iron, all right, the ferrous ion of iron. The reason why we say ferrous ion, because it's easier than saying iron. The ferrous part is 2+, and it can then react further to form a 3+ ferric ion. So ferrous is on the way to ferric. Ammonium is a non-metal polyatomic ion. Okay, it's nitrogen with a bunch of hydrogens. That has a +1. All these guys here, your halogens, are informed by the periodic table. They're in that group, okay, that group that can only accept one electron, so they become -1 charge. So, ionic compounds dissolve. In fact, if you heat them up or heat the water up enough, any ionic compound can dissolve in water. There is a reason for this, and I'm going to demonstrate something in a minute to show you what I'm talking about. Now, water is slightly charged, believe it or not. It has a positive and a negative end. We'll explore that further when we look at covalent bonding. Water attracts to the ion particles in the lattice, and what will happen is it will pull them away. It'll get inside and start pulling them away, and that allows for the salt to dissolve in water. Sodium chloride is a classic example. There's a ton of it in the ocean because the water can get in and break them apart because water is slightly charged. Now, just to demonstrate this, I'm just going to turn the lights on for a bit.
We did this in physics.
Oh, you did?
Yeah, in the first period. Shut up.
First period. Yeah, that's weird. Okay. So, those of you who didn't do physics, you get a magical wand like this. It's a glass rod. And I'm going to charge it up. Okay, cause some static to build on the rod, get it charged. Okay, the same sort of energy that causes you to get that staticky shock when you've got new carpet. What was that in English? I heard rah, 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 rah. Yeah, there's a reason why I'm not doing that, because it's on camera. So, now if I pull that wand, I can now bend the water.
Brownie's result was much better.
Okay? So I can bend the water without touching that column. Might charge it up a bit more. That's wrong, isn't it, Townley? So water, this is just demonstrating that water is completely charged. So I'm causing the particles that have charged along this rod to repel the water, to bend it. So if I can bend it out here. Now I've just discharged it. Sorry? See if I can do that. I don't want to go there. All right, give it a go. See if you can get the water out the sink. Wingardium Leviosa. Hi, Cassie. This is Isaiah, who's currently stroking the rod. That's the weirdest looking thing.
I'm on camera too.
No, I'll pull the camera out this way. Okay.
It's not even working at all.
Oh, over here.
Terrible. Go, harder.
It's actually.
When the lactic acid.
He is.
Oh, come on.
No, now you've discharged it. So as soon as you touch metal, you've lost all that charge there because it's transferred to the metal.
I thought it'd be working it slightly better.
Okay, I think we might stop that
Yeah, maybe.
before you hurt yourself. But yeah, you don't need to touch water to move it around because it is charged. And because it is charged, it can pull apart those charged particles in an ionic lattice. So if we look at my diagram here, I turn those lights off. And this way, thank you all. Okay. The oxygen end of water is negatively charged, and this attracts the positive metal ions. The hydrogen end of water is actually positively charged. The reason is because of electronegativity. Remember how oxygen has high electronegativity? It pulls electrons better, okay, than most other elements. So what actually happens is along the bond it has with hydrogen, it pulls the electrons more towards itself. And as a result, you get the slight negative end because there's more of an abundance of electrons at one end of water. And because hydrogen is having its electrons pulled away from it, it ends up having a slight positive end. So as a result, it can pull that lattice apart. So the positive end attracts the negative particles, and the negative end attracts the positive particles, dissolving in water. Now, if the force between the ions is too strong, and one classic example is aluminium oxide. Aluminium forms a 3+ charge. It's a strong charge. And oxygen has a 2- charge. When you have those sorts of situations, very hard to pull them apart from each other. So that's why we say it will not dissolve. It is insoluble, and you'll get a precipitate forming in that case. Now, precipitates can disappear. You just need the water temperature to rise. Okay, if you increase water temperature, you can change the solubility of things. But ordinarily under room temperature, aluminium oxide will not dissolve despite being an ionic complex because the charges are just too strong for the water to pull them apart from each other. But sodium chloride, where you just have a +1 and a -1, that can pull apart. It's infinitely soluble. It's what we call an infinitely soluble salt. Okay, it will do it every time. Okay? And these notes, of course, will be up on DayMap. I want to look now at the physical properties, and it's important that you know this because this is how you're going to differentiate ionic bonding from metallic, and then when we start looking at covalent bonding. Things to note. They do not conduct electricity in what we call the solid state. They must be dissolved, okay, or they must be molten. When we think about electricity, it's really a flow of charged particles. Okay? Normal electricity is electrons flowing through something. Now, when they are presented with ions in a solid state, the electrons can't pass through because they're being held by the non-metal. They're not being passed along to the metal. But when they are dissolved, okay, when those salts are dissolved, you have all these particles swimming about. The electrons can use them to bounce from one to the other. Those positive charged metal ions, they'll use those positive charges and they'll bounce along. So you can actually conduct electricity providing the particles are free to move. And that's the same for in the molten state. When the ionic compound is melted, it's in a liquid form that allows the particles to move. When they're in a solid, they're not moving. They're locked in place. And that prevents electrons from getting through, so you cannot conduct electricity. Which is different to metals. Because they've constantly got that delocalized cloud, you can always conduct electricity in metals in all states. Question, Christoph?
From this diagram on the board, is it suggesting that like distilled water doesn't conduct electricity?
Correct. Distilled water will not conduct electricity. It is actually the particles in water that conduct electricity. Okay? Water itself cannot conduct electricity. It is slightly charged, as I said, but the electrons aren't going to do anything. They're too far apart, and the electrons in the H2O molecule are locked in place. They don't want any more. They won't accept any more. So as a result, you cannot, if you've got pure water, you cannot conduct electricity with it. The actual electrical conductivity of water is a result of all the salts that are dissolved in that water and other particles, okay? So salt water, all right, is extremely, has the potential to conduct electricity quite well. Now, but it's the sodium chloride conducting that electricity, not the water. When you have an accident, or when people have accidents in the bathtub with like a hairdryer or some stupid thing, okay, what the electricity that's causing them to electrocute themselves is as a result of all the salts dissolved in the bath, not the actual water itself. So distilled water doesn't conduct, and that's why we use a lot of distilled water when we're dealing with electrical equipment. That's why you should use distilled water in the jets on your car, okay, that clean the windscreen. Yes, well, you should also use acetone for that, but yeah. You should, yeah. In chemistry, we will start in next semester when we start using all the fancy equipment. We'll wash it, coat it with distilled water. Yep.
Do you use distilled water on your car when you ride about it?
I do. I make sure. Not when I'm washing the car, but in the jets.
Yeah.
The little jets that you flick on. I have a Mazda 3. Now, ionic bonds have moderate to high melting points because of those electrostatic charges. They really love to hold on to each other, so they're hard to melt to begin with. They are crystalline in the solid state, as evidenced by that lattice, and they are also very brittle. Okay, they crumble like a crunchy. So the reason for that is if you push one layer of the crystal across, you end up aligning like charges, and when you've got like charges aligned with each other, they will repel, and that's why it breaks. Okay, metals don't do that because they're constantly in a neutral state, if you will, because the metal ions, the positive ions, are surrounded by electrons. So it doesn't matter which way you bend it. But with salts, okay, as soon as you align those like charges, the salt will break. Kind of, yeah. Well, that's what it is. It's electromagnetic forces that are responsible for this attraction. So by that same token, yeah, like charges repel, opposites attract. We know that. Okay. I think that's all I really want to look at for ionic bonding at the moment. Those physical properties. And make sure you know them and can compare them with metal properties. In particular, the most important thing is the conduction of electricity and recognizing melting points. I'll stop the video there.